that's a very difficult question, because when you look for asteroids, okay, you have what we call selection effects. You can't do a search for asteroids and find all of them. You can only find a subsample of them. Right? It's like if you're going fishing, you can't find all the tuna in the sea. You can only find a few, and then you try and estimate how many tuna there are in the entire ocean based on the few tuna that you actually caught. But when you do that, it might seem simple. You go fishing in 1 square kilometer, you catch all the tuna in that 1 kilometer, and then you say, okay, but there are 3 million square kilometers on the Earth, therefore it's very easy to figure out how many tuna there are on the planet. But the distribution of tuna is not constant. There are not as many tuna at the North and South Pole as there is at the equator. And even in your 1 kilometer that you look, when you were fishing over here in one corner of your 1 square kilometer, as soon as you fished some out, some more came in. And so you have to take all these things into account when you want to try to estimate how many tuna there are in the ocean. And then it's the same problem with asteroids. So it's not a very simple problem. And it's one of the things that I specialize in. So in the rest of my talk, I'm going to be talking about absolute magnitude sometimes, and diameter is easy. But when I talk about absolute magnitude, it's the term we use in planetary astronomy to talk about the size of an asteroid. An asteroid of an absolute magnitude of 18 has a 1 kilometer diameter. And the thing to remember is that a 10 times change in diameter corresponds to a change in absolute magnitude of 5. So if 18 is 1 kilometer, then 13 is 10 kilometers, and 23 is 100 meters. Okay, so it should be relatively simple. So now if we look at the semi-major axis distribution of asteroids in the main belt, so I'm talking about that, so remember, semi-major axis is the distance from the sun in astronomical units. So this is the distance from the sun of the asteroids, and this is over all h, or equivalently all diameters. It looks like this is the distribution of asteroids as a function of distance from the sun. But in fact, that has got this problem as I described with the tuna. It's a very biased situation. Okay? The real distribution of asteroids, we can see if we limit to just those objects with an absolute magnitude less than 13, which corresponds to a diameter bigger than 10 kilometers. So we think we know where all the 10 kilometer diameter asteroids in the solar system are located. And if we look at them, we see that there's this very different distribution here compared to what we saw over here. That's all due to the problems with identifying asteroids from the Earth. And it's even worse than that, because you would hope that if all the asteroids were the same, had the same reflectivity, that they were the same brightness, then it would be pretty easy to figure out this distribution from this distribution. But in fact, it gets even worse, because the asteroids that are closer to us have the highest reflectivity, and the asteroids that are furthest from us have the lowest reflectivity. So the further away they get, the harder they are to see. Okay? And so we have to take all these things into account when we want to try and identify how many near-Earth objects there are. So where do these near-Earth objects come from? How do they get into near-Earth object space from the main belt? Well, there are many different sources of the near-Earth objects. The one I will talk about is this 3-to-1 source here. The 3-to-1 source means that an asteroid, if you were to have an asteroid that had a semi-major axis of 2.5 AU and an eccentricity of 0.3, and we went over those terms earlier, then what would happen is that asteroid would make 3 orbits around the sun every time Jupiter made 1 orbit around the sun. And Jupiter is the most massive planet in our solar system. And so that means that the asteroid goes around 3 times, Jupiter goes around once. And so every 3 revolutions of the asteroid, it comes into the same orientation with Jupiter. And Jupiter then tugs on it in the same way, at the same position in its orbit all the time. It's like if you're trying to push a child on a swing. You know, you can have a child on a swing, and just with your one little finger, you can touch the child. And as long as you touch the child at exactly the right frequency, you build up a large swing for the child. Right? And it's the same thing with Jupiter. Jupiter tugs on that asteroid in the same way, the same frequency, and it changes its orbit. So instead of just staying at this location, its eccentricity will increase until eventually its eccentricity becomes large enough that it can approach the Earth. And once it can approach the Earth, then the Earth's gravity begins to affect it and changes its orbit as well. So let me show you an example. This is a numerical simulation, but it's very accurate, of what happens to how the semi-major axis and eccentricity of asteroids evolve as a function of time. It's a kind of a complicated figure. This is semi-major axis, distance from the sun. This is the eccentricity. So this is a circular orbit. This is a very, very straight orbit, or a line. And these lines here represent different things. Anything there is outside of the Earth's orbit. Anything in there is an Earth-crossing orbit, and anything in there is inside the Earth's orbit. So the Earth is right here at 1 AU astronomical unit from the sun and 0 eccentricity. Now this here is a set of synthetic asteroids that are in one of these NEO sources. And let's just run a simulation here to see what happens. This is time in millions of years, and this tells how many of these asteroids that start off here are remaining. Okay, how many are left? How many have not hit the sun? How many have not hit one of the planets or been entirely thrown out of the solar system? So as we see, in just 1 million years, these objects change from just being here to having their orbits distributed all over this figure. And you can see that after just 8 million years, we've lost 80% of the asteroids. 80% of the asteroids we started off with hit the sun, hit a planet, or were entirely ejected from the solar system. And after 10 million years, it's almost 85% of the asteroids are gone. So you can see that things in the main belt can be stable for a long period of time unless they are in one of these NEO sources. If they are in an NEO source, then they very quickly go into the NEO region and are lost. So what I did in some research about 10 years ago, is each one of these sources has got its own fingerprint on where objects move to in our solar system. So there's one source, well, we talked about the 3 to 1, so let's talk about that. So this 3 to 1 source I told you about, all the objects in the 3 to 1 start off at 2.5 astronomical units with low eccentricity. But very quickly, they fill up this entire space. And this here is kind of a fingerprint of where these objects appear in orbit element space. And each one of the sources has its own fingerprint. So what we can do is we can create a model just of the orbit distribution of the objects and their size that takes into account the source distribution from each one of these 5 different sources. So really we're sort of trying to do a match between the fingerprints of the real source, of the real near-Earth objects, and the fingerprints from each one of the possible sources. And I'm not going to describe this because it's too complicated, but what we did, at 10 years ago, it was quite incredible. It took a lot of computing power to figure this out. We did a 4-dimensional fit in the semi-major axis, eccentricity, inclination, and size, absolute magnitude. And a 4-dimensional fit took place over 75,000 bins of data. Okay? And of those 75,000 bins of data, there were only 138 NEOs known at that time. So most of our bins had 0 objects, and only 138 bins had 1 object. And yet, even so, we were able to do a fit using something called a maximum likelihood technique that allowed us to fit our observed distribution of near-Earth objects to these source regions. And our fit was quite good. Our fit is the model that we got out of our fit is in yellow. The actual data is in the purple here that you see. And you can see that despite doing a 4-dimensional fit with so little data, we were able to still get a very good representation of what the real near-Earth objects look like. This here shows what the final distribution looks like in inclination, eccentricity, and semi-major axis. And this here shows their size distribution. Our size distribution implies that there are about 1,000 near-Earth objects larger than about 1 kilometer in diameter. Now, I don't want to talk about that. our model allows us to calculate how many objects are actually in each one of the sources. And so it turns out that the outer belt region has got the largest number of objects. Notice how much of this region here is this red outer belt region, and how little of it is this nu-6 and 3-to-1 resonance. But if we look at the injection rates, this is how many near-Earth objects get injected from each one of those sources per million years. You can see the outer belt injects a lot of objects every million years, and the other sources do not inject so many. But when you actually look at how many, in the current NEO population, how many objects came from each one of those sources, notice here, very few objects apparently come from the outer belt. That's because anything in the outer belt that got ejected from the outer belt into the near-Earth object region is on a kind of orbit that allows it to come very close to Jupiter. And Jupiter is a very massive object, and it manages to gravitationally throw away the particles, the asteroids, very quickly. So even though the outer belt has a lot of objects and spits a lot of them into the near-Earth object space, they do not last long because they come into contact with Jupiter. So right now, we're at the point where we know, actually I made this figure a while ago, right now we're at the point where we know 90% of all the objects that are Amors, Apollos, or Ottens, and we only know about 10% of the objects that are entirely interior to the Earth's orbit. That's because if they're entirely interior to the Earth's orbit, they're always in the direction of the sun. And we can't look in the direction of the sun to find asteroids. So we do not know where most of those objects are. Now I like this movie here. This is a movie that I made up showing what the 1,000 largest near-Earth objects look like if you're on a spaceship that goes, that is stationed above the Earth, looking down at the Earth, and following the Earth around on its orbit. Okay? So this here's the Earth. Each one of these green circles represents a near-Earth object, and you can see that the Earth is in a pinball machine or a beehive of activity of these near-Earth objects. And because of the strange frame that we're looking at, the strange way I've done this video, the Earth is always facing the sun, so you see only the right side is lit up because the camera is rotating around as it follows the Earth in its orbit. But you can see that these near-Earth objects can come very close to the Earth, and we live in a very dangerous place. But there are problems with these models that we've created. Our model predicts 310 plus or minus 40 of these Amor-type asteroids, but the known number is 470. Okay, so that's a big difference. Okay, it's a 4 sigma difference. So it means that our model must be wrong. Of course, we did our model 12 years ago. Another problem with our model is that our model really only works to about 1 kilometer or maybe 200 meters in diameter. By the time you get down to the smallest sizes, by the time you get down to things that are just 10 meters in diameter, there's a factor of 100 difference in the predictions for the number of near-Earth objects. So we don't know whether or not there's 1 million or 100 million near-Earth objects 10 meters in diameter. That's too complicated to describe. And another problem with our model is that if we look at the number of near-Earth objects as a function of inclination, this is the real known distribution. This blue line here is our prediction, and this gray shaded region here is the prediction of another group that used a different technique. So you can see that overall, we don't do too bad here in reproducing or agreeing with the other group, but they have this big bump here. And that big bump is due to a particular source of near-Earth objects that we did not account for. Okay, so there's lots of things wrong with our model that now we want to go and improve. So let me see what time it is. It's I have a few more minutes. Yeah, okay, I'll try and go quickly. So what is being done about it? How do we fix our models? How do we improve our knowledge of the asteroid impact hazard? And I'm going to describe 2 ways. One is this Pan-STARRS project that I'm working on. It's still, I would say right now, it's looking unlikely that it will ever be done. But 9 years ago, I joined the University of Hawaii to build this system. And because it is unlikely to ever be done,
I'm not going to spend much time talking about it. But it was supposed to be 4 telescopes, each telescope 1.8 meters in diameter. And one of the great things about the telescope is that it uses something called orthogonal transfer CCDs. I hope most of you know that inside your digital camera there's something called a CCD, which is the equivalent to the photographic film inside your camera. And most of these CCD cameras, they've got a pixel structure that allows them to move the charge that represents the light either up or either down or right. Okay, and they can only do it once. They basically take an image and then you read out the image by moving the pixels down and then to the right. But the great thing about the orthogonal transfer CCDs is that you can move the light, the charge in the pixels, up and down, left and right, and you can do it as the image is being taken. So as the image of the star is moving around on a CCD because the telescope's not tracking properly or because of other problems, we can move the light that represents the star on the CCD in exactly the same way to compensate for these errors. And so we've taken images here that show what the sky looks like without the orthogonal transfer on, and then with the orthogonal transfer on. And you can see that this star here that looks fuzzy in this image becomes quite clear in this image, right? And this object right here that you can barely see, it gets hidden by my laser pointer, becomes clearly a star in this image right here, right? So this orthogonal transfer is a sort of way of doing image stabilization on the big camera as we're taking an exposure. So we're unlikely that we're ever going to build the 4-telescope Pan-STAR system, but we do have a Pan-STARRS prototype telescope working. We call it PS1. PS1 is now operational. It's been operational for about 2 years, and it's run by a consortium of about a dozen different universities. It's currently producing a lot of data and finding a lot of asteroids. The location is here in the Hawaiian island chain. To give you some orientation, Quito is off in that direction. And the Pan-STARRS headquarters is in Honolulu, where I have worked for the past 9 years. Right now we have the Pan-STARRS 1 telescope. The prototype is on Maui, on the summit of a volcano there called Haleakala. And we hope very soon, by the end of this year, to have the second telescope working on Haleakala as well. And then hopefully, somewhere in the distant future, if we can find somebody to give us the money to build it, maybe the Ecuadorian government would like to contribute $40 million, and then you can all have jobs, right? Come to Hawaii and work on the Quito Pan-STARRS telescope, but we don't know when that will be built or if it ever will be built. But the amazing thing about Pan-STARRS is its field of view. If you knew anything at all about telescopes, a typical telescope field of view is about that big, okay, relative to the moon. We all know how big the moon is in the sky, but if you use a typical telescope, that's how big its field of view is. That's how big its image is. Okay? The Pan-STARRS field of view is as big as this entire array here that you see. And so, we can fit the moon onto a tiny portion of our camera. And something as big as the Andromeda Galaxy, which means something to the astronomers in the audience, fits entirely onto our camera.